Hey class, I'm Mr Thornton and I'm going to help you succeed in your GCSE. This lesson, Household Electricity Part 1, Safety. A lot of people have requested this topic, including Isaac Shelton, Queen Kylie, Crev M, Nujoma, Chloe Botton, Cerebral Assassin, Thembe Moyo, Russell Chings, Charlton Home Days, Alan Phillip and Nishu Gurung. Thanks guys. If you've got a topic which you'd like me to cover, then just leave a comment below. Here in the UK we have a 3-pin electrical plug. These two smaller pins here are the live and neutral pins. They're responsible for the delivery of electricity to the appliance. This larger pin here is the earth pin. It's not always used though. It doesn't need to be used, for example, if you've got an appliance which is relatively low power and is double insulated. This hairdryer, for example, it's got an entirely plastic body, so even if there were some sort of fault in here which caused a wire to short out against the surface of it, the plastic body would prevent me from getting an electrical shock whilst I held onto it. So in this particular device, although this is a metal pin, it probably isn't actually connected. It's an entirely molded plug here, so I can't open it up to see, but I'd be very surprised if that was actually connected to anything. Sometimes you get it where it's even more obvious. This Wi-Fi hub here has a completely plastic earth pin. This earth pin does nothing in this appliance because, again, the whole thing has a plastic body and it's very low power, so there's no danger of me accidentally getting electrocuted from this, even if there is a fault with it. So you need, as a minimum, the live and the neutral pins, and sometimes there will also be the earth pin involved as well. Inside our electrical cable, there will be a minimum of 2 or possibly 3 wires. Each one corresponds to one of the pins. So there'll be this outer cable to protect it and to take the strain and the load, and then these are responsible for actually carrying the electricity. So we've got double protection. Again, they're double insulated. At a minimum, you will have a brown wire here, which is the live wire. You'll have a blue one, which is the neutral, and you may have this green and yellow wire, which is the earth wire. Now the brown wire, that is at 230 volts. That is carrying mains voltage. Even if this weren't connected to an appliance, even if I just took this plug as it is and plugged this into the mains, so this is not part of a circuit at the moment, and just plugged into the mains, no electricity would be flowing through this at the moment because we haven't completed the circuit. This is still dangerous because that wire would still be live, and if I were to touch it as I am doing now, I'd almost certainly get an electrical shock. I'd get an electrical shock which would be big enough that it could cause me serious injury or possibly even death. So even when there isn't a circuit here which is switching this off, this live wire can still potentially be dangerous. So that's at 230 volts. The neutral wire here should be at around about 0 volts normally. This is the return path for our electricity. Remember, electricity needs to go out of the power supply, through the appliance, and back out of that appliance back to the power supply. Think about it being a little bit like a battery or a cell where the electricity comes out of one side, right through whatever we're using it for, and back into the other side of that battery or cell. Well, same thing's got to happen here. So the electricity comes out of this one and it's going back down this one. But normally this will be at approximately 0 volts. It may be slightly higher or slightly lower, depending on all sorts of different things to do with the electricity supply, but you don't need to worry about them. You just need to know that this should be at around about 0 volts, and this one, in the UK at least, will be at approximately 230 volts. The earth wire shouldn't be involved in doing anything at all in the circuit so long as everything's fine. This is there purely for faults. So again, normally this should be at 0 volts. If there is a fault, then that voltage may very briefly rise and then it should drop back to 0 again because it should trigger the fault sensing devices within our circuit, which will make sure that that appliance is knocked off. To consider how appliances are automatically knocked off, what we need to do first is consider some of the things which might go wrong. So if I open up this plug, by unscrewing the central screw in it, and we take a look inside, we can see the layout of where the different wires go. And we can also see what could potentially go wrong. So to run you through this, we have a wire for each one of the different pins. The brown wire, the live wire, is connected to, when we're looking at it from above, the bottom right pin. So that is BR for brown and BR for bottom right pin. Actually, in practice, it might sometimes go up a little bit towards the fuse, but it is always going to the right pin. And that pin is always going to be at the bottom right. It's just that it's got to connect via this fuse here. And the only way to fit that fuse in is often having it raised up a little bit there. But BR, brown, BR, bottom right. That's the key thing to remember. Same thing with the blue wire. BL is blue and it's bottom left. It goes to the bottom left pin. No fuse involved here. The fuse is always connected to the live wire because remember, that's the one at 230 volts. That's the one which we want to be able to disconnect if there's some sort of fault. And finally, our earth wire goes up to the earth pin up here. Now, occasionally they might ask you to identify things which are wrong with a plug. So let's run through some of those. Firstly, and perhaps most obviously, the wires could be connected the wrong way round. In particular, the blue wire and the brown wire could be connected back to front. This is why the wires are coloured blue and brown, so that you can remember BL goes to the bottom left pin and BR goes to the bottom right pin. If it's on an exam paper and it's printed in black and white, they will normally label what colour those wires are or give you some indication of which one's which so that you can tell. Because if they didn't tell you which one was which, then you wouldn't be able to figure out which way round they should be connected. The next possible problem is that you could have exposed wires in the plug. A little bit of exposed wire, a millimetre or two, just where that wire is connecting to the pin, so long as it's nowhere near any of the other wires that might be exposed, that's not a big problem. But if it's a large amount of exposed wire, if it's very obviously most of the wire in there that's exposed, then those wires could be causing short circuits from one to the other. That's going to be inconvenient because it's going to mean the electricity isn't going into the device which you want to power, and it's also going to be dangerous because you could get a large current flowing. That means things could get very hot, maybe something could set on fire. It's difficult to say exactly what the likely consequences would be, but they wouldn't be anything which you'd want. Next, notice down at the bottom of the picture here, we have the cable grip. This is supposed to grip the outer part of the cable and hold it in place so that if you trip over the wire, it doesn't yank live wires out of the plug and potentially electrocute you. That cable grip should be over the top of the cable and gripping it, hence the name cable grip. A common fault is that the cable grip is underneath or it's totally missing. Another thing which can go wrong with the cable grip is it won't be gripping the outer part of the cable. That outer part of the cable is just there to take the strain. It is not there for any other reason. The inner cables are already insulated. But if the cable grip is going over the inner cables and someone tripped over that wire or yanked on it, then they could again potentially pull live wires out of the plug. So the cable grip should be around the outer part of the cable, not any of those inner wires. Next, the fuse might be the wrong type of fuse, or it might be missing, or it might have been replaced with something stupid like a piece of tin foil. If it's not there, then obviously you've got a break in the circuit, the live wire is disconnected from your appliance, and it wouldn't work. If it's been replaced with the wrong type of fuse, then you could potentially either get the fuse melting if it's too low a value, or you could get the fuse not melting when it should do if it's too high a value. I'll talk in a minute about how we choose the right type of fuse. If the fuse has been replaced with another conductor like a piece of tin foil or a piece of wire, then the circuit will work just fine, but you are removing that safety feature which is there to knock off the circuit if there's a fault. So that is just as dangerous. Also look out for any of these wires not actually being screwed in to the relevant places on the different pins. If one of them is loose, then at best, again, the circuit isn't going to work, and at worst you could get short circuits, and that could cause all the problems which I've mentioned already. Finally, the casing of the plug could be broken, which could potentially expose live parts of the circuit to a person's hand, and there's a danger that they could touch them and electrocute themselves. So really our two key dangers boil down to the possibility of someone touching something which is live and becoming a part of the circuit themselves and being electrocuted, or to things overheating because too large a current has flowed. Now I'm going to focus on those large currents flowing first and how the safety features stop that. The first one, the fuse, is very, very simple. The fuse is just a piece of wire which is designed to melt when it gets hot. So if a large current flows through it, it tends to make it warmer. When currents flow through anything, they tend to make them warmer. And this is specifically designed to melt above a certain current. This is how we choose what type of fuse to use. Once you've figured out what the current's going to be, and you'll do some sort of calculation, perhaps with V equals I times R or Q equals I times T, but you'll be doing some sort of calculation to figure out what that current will be. If the fuse is too high a value, then it won't actually melt if an excessive amount of current is flowing. If it's too low a value, then it will melt when a normal amount of current is flowing. So what we want is the smallest value of fuse which is still bigger than the normal current. So if we had a current of 4 amps flowing and we put a 3 amp fuse in there, that 3 amp fuse is going to melt. It's not going to be any use because our normal current, our 4 amps, is going to be above that and it's going to melt it more or less straight away. If we put a 13 amp fuse in there, well then if there's a fault, there's a big difference between 4 amps and 13 amps. There is going to be quite a lot of current flowing potentially before that fuse actually melts. The next value of fuse up from 4 amps is 5 amps. So in this country we have 3 amp fuses, 5 amp fuses and 13 amp fuses for most of the fuses which we might use in our homes. So 3 amp is going to be too small, 13 amps is going to be way too big. You just go with the next biggest one, which in this case would be the 5 amps. That means that under normal operation at 4 amps, the fuse will be just fine. It's not exceeded the maximum amount which it can take. It could take a bit more than that. But if a lot more current starts flowing, it's going to be way over that 5 amps and we're going to melt the fuse. So what could cause a large current to flow? Well, basically, any time the electricity is able to flow without having to power the appliance. So that is, if you've got a short circuit, live wire touching neutral or live wire touching earth, if you've got some sort of short circuit within the device where there's a piece of metal in between the live and the neutral or the live and the earth, both of those will cause large currents to flow because basically there's just a nice conductor in between those two things which are carrying the electricity. There's nothing else. There's no real resistance there except for that bit of metal which is going to have a very low resistance. So you will get a very big current flowing if you've got very low resistance. And those are the most common types of faults. It's where you've got two wires which are bare for some reason, either due to a fault when it's been assembled or just through wear and tear. But those two wires make contact with each other and then a large current flows between them. And that will melt the fuse. It can also happen if a live wire touches a metal case. This is why we have an earth wire. The earth wire will also be connected to the metal case. So that if a live wire does touch it, or if a live component does touch it, then a large current is going to be able to flow through that metal case. Now that may sound counterintuitive, that surely we don't want a large current flowing through a metal case because someone could touch that. But the thing is that large current only flows for a very short amount of time, a few seconds at most, and that large current then melts the fuse and knocks the appliance off. So the earth wire is always connected to the metal case of a device, and if you've got any appliances which have a metal case, they should have an earth wire connected to the inside of that metal case. It will normally be out of sight, so it'll look nice, but it will be there to protect you, and if there's a fault, then a large current will be conducted down the earth wire through the metal case, which will melt the fuse almost straight away. So to summarize that, either a short circuit because you've got two bare wires touching, or if you've got a live wire touching a metal case, both of those are going to give you a big current and that will melt the fuse. That's all there really is to the fuse. One more thing which it's worth bearing in mind when you're thinking about the current is the thickness of the wire on the appliance. If an appliance only has a relatively thin wire going to the mains from the plug, then it's probably only going to be carrying a relatively small current. Whereas bigger currents travel better along thicker wires, so that should give you some idea of whether it's going to be using high current or low current. Fuses in plugs are very useful, but they are a last line of defense. There is another line of defense which we can use as well to make things extra safe. And this is what a lot of people still refer to as a fuse box. It used to be that where the electricity came into your home, you had another set of fuses. So one set of fuses for the lights, one set of fuses for the sockets, and so on. These were a little bit fiddly because, of course, when one of those fuses blew, you had to replace it with another fuse. People didn't always have the right sort of fuse. Quite often, people would deliberately connect something across that fuse which wasn't going to melt just because it was inconvenient. Nowadays, we have something that's a lot better. We have something called an RCCB. That is a residual current circuit breaker. These are the switches which you probably still refer to as a fuse box. This is mine. Each one of those switches controls one of the major circuits in my home. So again, things like sockets, things like my water heater, things like my lights. You can see that they're all labelled in this case. If there is a fault in one of those circuits, it might blow the fuse in an appliance, but it will also trip the RCCB for that particular circuit. Now, I'm sure you've experienced this yourselves, where a light bulb has blown and it's knocked out all the lights in that room, or possibly on that floor, or possibly all the lights in your home. It can be inconvenient, but all you've got to do is flip the switch to reset it. So, for a start, it gets rid of that whole problem of people trying to connect something else across there because they're sick of the fuse blowing. They've got a switch instead. It's a lot easier to reset. Plus, an RCCB reacts a lot faster, way faster than a fuse. A fuse can take seconds. An RCCB can take a fraction of a second to respond. And so there is much less chance of you getting seriously electrocuted if the electricity is going through these instead. The RCCB is just doing a very simple comparison. It's comparing the current into the electrical circuit from the power supply along the live wire with the current back out of the circuit along the neutral wire. And these should be the same. Remember, with any power supply, the amount of electricity, the amount of current which you get coming out of the power supply should always be exactly the same as the amount of current going back into the power supply. It'll have lost its energy that will have been used by the devices in the circuit, but the current should still be the same all the way around the circuit. And so that's all the RCCB is doing. It's checking that the same current is going out as is coming back in. If it's not the same, that's when the switch triggers. All that you need to know about an RCCB is that it's easily reset, which means that you can use it over and over again. It's fast, way faster than a fuse, which makes it a lot safer, and that all it's doing is comparing the current in and the current out, and if they don't match, then it triggers. However, it's possible that your teacher has taught you how it works. That did used to be on previous versions of the specification from years ago. There was even a PowerPoint which, I'm not sure who it was who made it, but I do know that it ended up on the computers of an awful lot of physics teachers who I know, and it did explain how the RCCB works. So I'm willing to bet that it's possible that some teachers are still teaching that, but you don't need to know it. You just need to know that it can be reset, it's fast, and it's comparing the current in and the current out, and if they don't match, then it triggers. I hope that video really helped you. To see what else I can help you with, there's lots more videos to check out on my channel. Scroll down the main page there to see I've already sorted them into playlists to help you find a video you need. You can also check out my revision guides, which cover everything you need to know for the exam. They feature links to my videos, revision tips, cover both foundation and higher tier, and unlike a lot of revision guides, they also point out what you don't need to waste time learning. If you want to check your learning, try the SnapQuiz website and app, which allow you to identify which areas you need to spend the most time learning. Remember, this is the only YouTube channel which brings you the teachers, the textbooks, and the tests all on your terms, on mobile phone, tablet, or computer for you to revise when you want and how you want, even immediately before you go into the exam. All of these links and any others for this video will be down in the description. Lastly, it really does help my channel if you want to leave likes, if you subscribe, or if you know someone else who's having trouble, tell them to search for Mr Thornton. Good luck in your GCSEs everyone, and thanks very much for watching.